The night of May 16, 1943 arrived cold and clear over the industrial heartland of Nazi Germany. Over the Möhne Dam in the Ruhr Valley, the air was thick with tension. Squadron Leader Guy Gibson, piloting his Lancaster bomber at precisely 60 feet above the water, low enough that the aircraft's slipstream kicked up spray beneath the fuselage, radioed his prepared message. Behind him, 19 other Lancasters droned through the darkness in formation, each carrying something that should not have worked, something that existing military doctrine said was impossible. A cylindrical bomb that bounced. For more than 2,000 years, humans had built dams to harness water, to generate power, to feed cities. The Möhne and Eder dams were no exception. They held back vast reservoirs that supplied water and electricity to the Ruhr, the industrial engine of Nazi Germany's war machine. Steel was smelted here. Ammunition was manufactured. The Reich's ability to wage war depended substantially on these walls of concrete and masonry. Military planners in Britain had understood this for years. Photographs showed the dams. Studies calculated that their destruction would cripple German production. But there was a problem. Conventional bombing did not work. The dams were defended with anti-aircraft guns positioned along their length. They were surrounded by torpedo nets to prevent underwater attacks. And they were built with walls so thick, so heavily reinforced with concrete, that standard bombs simply detonated on the outer face and dissipated their force in the surrounding air. A bomb needed to explode against the dam wall itself, ideally underwater where the shockwave could be transmitted through the concrete with maximum efficiency. No existing bomb could be delivered with that precision. No existing bomb could perform that feat. And so the problem sat on the desk of a man in Surrey, in a small office at Vickers Armstrong's Weybridge facility, where an engineer named Barnes Wallis was staring at the mathematics of something that everyone told him was impossible. The challenge seemed insurmountable. Conventional bombing had failed. Mine-laying from aircraft had been attempted and abandoned. Underwater explosives were ruled out. Germany's naval defenses made approaching the dams by water suicidal. What the military needed was a weapon that could be delivered by air, could approach the dam despite its defenses, and could explode at precisely the right moment against the concrete wall. The specifications were contradictory. They were, in the opinion of most military engineers, mutually exclusive. And yet, between 1941 and 1943, as Germany's grip on Europe tightened, the scientific and military establishment of Britain became increasingly desperate for a solution. The dams had to be destroyed. Otherwise, the war would grind on, and the industrial capacity of the Reich would continue to fuel the fighting. The existing solutions had all failed. You could bomb the dams from altitude, but bombs did not have the accuracy or penetrating power. You could attempt to bomb the lake itself, trying to create a tidal wave that would overwhelm the structure, but the mathematics did not support this. The energy dissipated too quickly. You could try to send specialist teams to place charges, but German security around these facilities was comprehensive. Every conventional approach had been examined, modeled, tested, and found wanting. The military establishment had largely accepted that the dams could not be destroyed. They were, in effect, unbreakable. This was the psychological and technical landscape in which Barnes Wallis began his work. The task before him was not merely to design a new weapon. It was to violate the perceived laws of physics, to create something that should not exist, and to do it in sufficient time to be useful in an ongoing war. The breakthrough came from an unexpected place. Wallis had been thinking about the problem differently than conventional military engineering. Instead of trying to design a bomb that could withstand impact and penetrate, he began to consider whether a bomb could avoid impact altogether. What if, instead of hitting the dam head-on, the weapon approached the dam by rolling across the surface of the water, bouncing like a skipped stone? The concept was deceptively simple. The execution was extraordinarily complex. The bomb would need to be precisely cylindrical, balanced to rotate in a particular manner. It would need to be released at exactly the right altitude, exactly the right speed, and at exactly the right distance from the target. Any variation would cause it to miss. Any miscalculation would render it useless. At Vickers-Armstrong's in Weybridge, under conditions of absolute secrecy, Wallace and his team began construction of the weapon. The cylindrical bomb was roughly 5 feet in diameter and weighed nearly 6,800 kilograms, roughly equivalent to 3 motor cars stacked on top of one another. It was constructed with exceptional precision from steel, with a specific internal structure designed to ensure that when dropped from the appropriate height at the appropriate speed, it would strike the water and bounce, with each bounce carrying it progressively closer to the dam wall. The rotational characteristics had to be perfect. If the bomb rotated too quickly, it would fail. If it rotated too slowly, it would likewise fail. Everything depended on precise engineering and exact calculations. The bomb was detonated by a hydrostatic fuse, a mechanism that would trigger the explosive charge only when the weapon had sunk to a pre-calculated depth. This was crucial because the entire strategy depended on the bomb making contact with the dam wall and then sinking alongside it before detonation. The explosive charge itself was approximately 3,600 kilograms of torpex, a mixture of TNT, hexanitrodiphenylamine, and aluminium powder. When it detonated against the concrete wall, the blast would be transmitted through the water with minimum loss of force, creating a shock wave that would fracture the dam from within. The design represented a synthesis of aeronautical engineering, ballistics, hydrodynamics, and explosives chemistry. Nothing quite like it had ever been built. The manufacturing process was distributed across several facilities, each producing components in isolation. Security was paramount. No single person knew the weapon's complete purpose. The cylindrical bodies were manufactured at Vickers-Armstrong's in Weybridge. The internal mechanisms came from specialist engineering firms. The explosive charges were prepared at a separate location. Only a handful of senior figures understood what was being constructed and why. The project consumed resources, labor, and intellectual capital at a prodigious rate. As the weapon took shape through 1942 and into early 1943, the question became whether it would actually work. The first test drop took place in April 1943 at Reculver in Kent, over the sea. A modified Lancaster bomber, its bomb bay specially adapted to carry the cylindrical weapon, descended to the required altitude and speed. The bomb was released. What happened next was captured on film and in witness accounts. The sphere struck the water and bounced again and again, traveling across the surface in a series of diminishing arcs before sinking. The principle worked. The concept that had seemed impossible, that military engineers had dismissed as fanciful, functioned precisely as Wallace had theorized. Further drops followed, each refining the technique, each building confidence that the weapon could be delivered operationally. The final preparations took place at RAF Scampton in Lincolnshire, where 617 Squadron, newly formed and selected for this mission, arrived in late April 1943. The aircrew were briefed, though initially without understanding the full scope of what they were about to attempt. The Lancasters had been modified extensively, armor plating removed to compensate for the weight and altered aerodynamic properties of the bouncing bomb, specially calibrated sights installed, and mechanisms created to carry and release the weapon at precisely the correct parameters. Pilots underwent intensive training. They had to learn to fly at extremely low altitude, maintaining exact speed and altitude above water in darkness, using only moonlight and special spotlights to judge their height. It was some of the most demanding flying ever required of RAF pilots. The margin for error was infinitesimal. On the night of May 16, 1943, 19 Lancasters took off from Scampton in 3 waves. Their route took them low across France and Belgium to avoid German radar detection. As they approached the Ruhr, anti-aircraft fire erupted. 2 aircraft were lost before reaching the target. The remainder pressed on toward the Möhne Dam. Gibson led the first attack run. The Lancaster descended to 60 feet above the water, the airspeed holding steady at 390 kilometers per hour. The bombardier released the bouncing bomb. It struck the water and began its sequence of bounces, rolling toward the dam wall while the Lancaster pulled up steeply to escape the anti-aircraft fire that erupted around them. The bomb reached the wall. It sank. Underwater, the hydrostatic fuse triggered. The explosion detonated against the concrete, and at 1:28 hours, the Möhne Dam ruptured catastrophically. The water that had been held in check for decades poured through the breach in a wall that rose 30 meters high. The torrent swept downstream, demolishing everything in its path. Powerhouses were obliterated. Factories were inundated. An estimated 1,300 people died in the immediate flooding. The destruction extended for kilometers downstream, a rolling apocalypse of water and debris. The remaining Lancasters proceeded to the Eder Dam and the Sorpe Dam. The Eder succumbed to further bouncing bomb attacks. The Sorpe, with a different design, did not breach, though it was heavily damaged. Of the 19 aircraft that departed Scampton, 8 returned. 53 aircrew were killed in Operation Chastise, as the raid was codenamed. It became known to history and legend as the Dam Boosters Raid. The immediate impact was profound. German war production suffered substantially. The disruption to power and water supplies set back armament manufacturing, affecting tank production, ammunition output, and aluminum smelting. German engineers expended considerable resources fortifying remaining dams against similar attacks, resources that might have been deployed elsewhere. The psychological effect was equally significant. A weapon that military science had deemed impossible had been successfully employed. German confidence in their defensive positions was shaken. The morale of the Allied air forces soared. The myth of German invulnerability took another crack. Yet the bouncing bomb's broader impact was more limited than its dramatic success might suggest. The weapon was tactically brilliant, but strategically narrow. It could only be employed against specific targets under specific conditions. The dams could only be destroyed once, and the follow-up raids intended to strike additional targets largely failed. The resource expenditure in developing and deploying the weapon was considerable, and it achieved one spectacular success rather than sustained operational advantage. German engineers rebuilt and reinforced the dams. By the end of the war, production in the Ruhr had largely recovered, supplemented by synthetic production facilities built elsewhere. If you are finding this interesting, a quick subscribe helps more than you know, and it supports the creation of more historical documentaries like this one. The bouncing bomb occupied a peculiar place in military technology. The Americans, working through their own development programs, had created bombs with conventional-shaped charges and sophisticated fuses capable of significant penetration. These were destructive weapons, but they lacked the innovation and precision of Wallace's design. The Germans had experimented with various specialized weapons throughout the war, but nothing comparable to the bouncing bomb had emerged from German engineering. The concept was distinctly British. It represented a particular approach to problem-solving that prioritized elegant engineering over brute force. Whilst American and German designs relied on incremental improvements to existing bomb types and mounting them in greater quantities, Wallace had created something fundamentally different. The concept was never truly replicated by other nations. The Americans did not adopt the bouncing bomb. The Germans had not conceived of it before the war ended. The Soviets, in the post-war period, showed some theoretical interest but developed their own anti-dam weapons based on different principles. The bouncing bomb remained a singular achievement, a weapon so specific to its purpose and so dependent on precise conditions that it never became a standard part of any arsenal. Yet it survived in the collective memory of the Second World War, immortalized in films, books, and popular histories as a triumph of British ingenuity and courage. The surviving examples of the bouncing bomb are remarkably few. Original examples are held in the Imperial War Museum and at RAF Scampton, where the raid was launched. They are displayed as historical artifacts, their cylindrical form seeming almost quaintly simple for a weapon that required such sophisticated engineering and planning. The mechanics that made them work are less visible. The internal mechanisms, the rotation control systems, the fuses. Museums have created cutaway models showing how they functioned, allowing modern visitors to understand the engineering principles that Wallace applied. The bomb itself became iconic, invoked in popular culture as the quintessential example of brilliant British engineering solving the impossible problem. The legacy of the bouncing bomb extended beyond the immediate tactical results of the Dambusters raid. It demonstrated that unconventional approaches to military problems could produce results when conventional methods failed. It showed that scientific and engineering ingenuity, when properly resourced and supported, could create weapons systems that did things previously thought impossible. The psychological impact of the raid rippled through both Allied and German military establishments. For Britain, it was proof that innovation could overcome German military superiority. For Germany, it represented another crack in the image of defensive invulnerability. Barnes-Wallis himself went on to design other weapons systems during the war, including the Grand Slam bomb, an enormous penetrating weapon weighing nearly 10,000 kilograms that was used against hardened targets late in the war. After the war, he worked in aircraft design, creating the Vickers Swifts and contributing to aviation development during the jet age. He lived until 1979, becoming a celebrated figure in British engineering and aviation history. But for most people, his name remained forever linked with the bouncing bomb and the Dambusters raid, the moment when an impossible problem had found an impossible solution. The Dambusters raid remains the most celebrated bombing operation of the Second World War, not because of the tonnage of bombs dropped or the area destroyed, but because it represented something more: the triumph of careful thought over brute force, of precision over power, of one man's refusal to accept that a problem was insoluble. The bouncing bomb was, in essence, proof that given sufficient ingenuity, sufficient resources, and sufficient courage, even the most formidable defensive systems could be overcome. The dams stood again, eventually. German production resumed. The war continued for 2 more years. But for one night in May 1943, a weapon that should not have existed, designed by a man who refused to accept impossibility, achieved something that military planners had deemed unachievable. The Möhne Dam, built to endure for centuries, fell to the ingenuity of British engineering and the courage of RAF pilots who flew machines at 60 feet above water through anti-aircraft fire to deliver a bomb that bounced. In that convergence of science, engineering, and human courage, something remarkable occurred, something that would echo through history, reminding future generations that impossibility is merely the boundary of what has not yet been imagined.